Hello and welcome to the last of the lectures in this week 5 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the previous lecture, we have looked at the importance of transitivity, so to speak. We have seen that whenever you have a composition, there is going to be transitivity lurking behind and vice versa. And we have also seen that transitivity is essential if you want to have closed groupings which are non-overlapping. What are we going to discuss in this lecture? So far, we have seen fuzzy similarity relations. However, there are also other functions that measure similarity or dissimilarity. For instance, the kernel functions in machine learning, or the distance functions, which can be thought of as the dual of similarity. In this lecture, we would like to explore some possible correspondences between these three functions, that of similarity relations, kernels, and metrics. We know what a similarity relation is. It's a reflexive, symmetric, and T-transitive fuzzy relation. Now, a note about the nomenclature and notation that we will follow in this lecture. We know fuzzy equivalence relations are also called as similarity relations. They are also called T-equivalence relations. In the literature, this is also a term that is used to refer to fuzzy similarity relations, where it is clearly marked what is the T, and hence you will talk about T-equivalence where the T is the T-norm. Hence, just to stay true to the notation that you will find in the literature, we will also move from denoting a similarity relation by R to that of E. This is a small adjustment that we will make for this lecture right now. Well, what are these kernels or kernel functions in machine learning? These are functions from a given set X cross X to R, which are symmetric and satisfy positive semidefiniteness. What do we understand by this PST? That if you actually pick n points, any number of them, for any value of n, and construct the gram matrix as k of xi, xj, we see that this inequality will be valid for constants coming from R. Now, let's look at a couple of examples. This is called the Gaussian kernel, which is e power minus norm x minus y whole square. And there's another example, which is the exponential kernel, which almost looks like the Gaussian kernel, but it's e power minus norm x minus y. Let's stay with these two examples for a little longer. Firstly, we see that these are also reflexive kernels. What do we mean by reflexive kernels? Just looking at them as binary relations, we see that k of xx is equal to 1 for both these kernels. This kg of xx is 1 and ke of xx is 1. Also, by their definition, you see that in fact they are actually functions from x cross x to just the 0-1 interval, which means you can look at them as fuzzy relations, and they are also reflexive, and as kernels they are also symmetric. So essentially, we could look at them as fuzzy compatibility relations satisfying the positive semidefiniteness. What is a pseudo-metric? Many of us must already be aware of this. So it's a function d from x cross x to 0 infinity, such that d of xx is 0, it is symmetric and satisfies the triangle inequality. We know that metrics are typically used where you would like to use a distance function. So a pseudo-metric is defined by these three properties. A pseudo-metric becomes a metric if it further satisfies this property. That means d of xy is 0 if and only if x is actually equal to y. Now, note that this function t is actually from x cross x to r plus. Just like in the case of f generators or g generators, where we could find its normed generators, that means normalize it, in the case when f of 0 is finite or g of 1 is finite, we could do a similar thing here too. Take this pseudo-metric or metric D, and we could obtain a normalized version of it, which we denote here by d dash as follows. Simply d dash is d by 1 plus d. Clearly, you can see that d dash of xx is 0, d dash is symmetric, and in fact it can be shown that d dash retains all the metric related properties of d. Now, consider this function capital D, which is defined as 1 minus d dash. Once again, this capital D is a fuzzy relation. Clearly, it is reflexive and symmetric. Of course, we might have some property related to that of transitive triangle inequality through this 1 minus function, but currently it suffices to note that this capital D is in fact a fuzzy compatibility relation. Now, moving forward, what is it that we are interested in? So we have a T-equivalence relation, which is essentially a fuzzy similarity relation satisfying T-transitivity. We have the kernel, okay, and the metric, from which we can also obtain a similarity kind of function, a fuzzy compatibility relation. Now, if you look at it, in E, what is important is T-transitivity. In the kernel, what is important is the positive semidefiniteness. And if you are looking at the metric, what is important is the triangle inequality. We would like to see if somehow these three properties can be related. In this quest, let's start with T-equivalences and metrics, and we would like to see if T-transitivity can be somehow related to triangle inequality. Recall the Lukasiewicz T-NOC, which is nothing but max of 0, x plus y minus 1. Bestek and Harris, way back in 1978, proved the following result. They said if you have a T-equivalence relation, which is T-transitive with respect to the Lukasiewicz T-NOC, so we call it a TLK equivalence relation, then if you define D as 1 minus E, this d of xy is 1 minus e of xy, then this d is essentially a pseudo-metric on x. This is a very interesting relationship between TLK equivalence relation and a pseudo-metric. So essentially we are saying if it start with a TLK equivalence relation, you can in fact get a pseudo-metric. Now, how do we show this? Remember, we have defined d as 1 minus e of xy. We also know E satisfies TLK transitivity. That means TLK of EXY is less than for all tuples x, y, z coming from x. Now what we need to prove is that this D is a pseudo-metric. Clearly, d of xx is equal to 1 minus e of xx. Since e is reflexively 0, clearly d of xy is also d of yx because e is also symmetric. Now what we need to prove is the triangle inequality of the function d. Now let's look at this. What are we given? We are given that it is TLK transitive. That means this property is valid. Now let's translate this. What is this? This is nothing but maximum of 0, e of xy plus e of yz minus 1 is less than or equal to e of xy. What does this imply? This implies, by substituting for e, since d is 1 minus e, we could write e as 1 minus d. So this is 1 minus d of xy plus 1 minus d of yz minus 1 is less than or equal to 1 minus dxy. Now this implies, by cancelling out these two things, what we have is maximum of 1 minus Now note that 1 minus dxz. D now is 1 minus e. So this is a function from x cross x to 0, 1. So this is always greater than or equal to 0. So now here either it is greater than or equal to 0 or greater than or equal to this value. So which means from here we get 1 minus dxy minus dyz is less than or equal to 1 minus dxy. Well, from here we see clearly that dxz is less than or equal to dxy plus dxz. This is essentially the triangle inequality of D. Now, it is also very easy to retrace these steps. So now look at it. If you are given a D which satisfies triangle inequality, then from there we obtain this inequality. From there we could also add this because D is actually a function from x cross x to 0, 1. And from here we can retrace this and we obtain this, which is essentially the T-transitivity of E. So what we have now is that if you have an equivalence relation which satisfies T-transitivity, that is a T-K equivalence relation, we have shown that the T-K transitivity in fact can be related to the triangle inequality of D, where D is 1 minus E. So this is one of the very first results which related the T-K transitivity with the triangle inequality of a metric, a pseudo-metric that you can obtain from E. A quick recall. So if you consider the additive generators of a T-NOC, which are functions f from 0, 1 to 0 infinity, continuous, strictly decreasing, f of 1 is 0, and of course f of 0 can either be infinite or finite. We know that we can obtain a continuous T-NOC Tf in this fashion. It is also called a generated T-NOC from f. Now what is interesting is, when you look at f of x is 1 minus x, you can either look at it as a negation, a fuzzy negation, or also a generator of a T-NOC. And we know that this actually gives rise to the Lukasiewicz T-NOC. Note, this is the result obtained by Bestek and Harris in 1978. Bernard Dabarts and Ratko Messier, they were quick to notice this and said, look, we are just using one particular generator. Is it possible to generalize this? So instead of asking for an equivalence, TLK equivalence relation, they took a continuous T-NOC Tf with additive generator F and looked at a Tf equivalence relation on X. So pick an E which is a Tf equivalence relation on X, where Tf is an F generator continuous T-NOC. Then if f were 1 minus x, we are taking it as 1 minus e. So now change it to f of e. And we were able to simply show that if you consider Tf equivalence relation, then by using this formula D as f circle E, f composed on E, we were able to obtain a pseudo-metric on X. So given a Tf equivalence relation, you can obtain a pseudo-metric. They also showed, so this also shows that Tf transitivity is again related to the triangle inequality of D, as we have obtained here. They were also quick to see that on the converse, if you start with a pseudo-metric D and pick any continuous T-NOC which is generated from an F and define a relation E as follows, f inverse of min dxy from f of 0, then they were able to show this is in fact a Tf equivalence relation on X. So essentially taking the triangle inequality and then be able to relate it to the Tf transitivity. That means we clearly see that this Tf transitivity is somehow clearly, it has a one-to-one correspondence to the triangle inequality of D as we have defined this pseudo-metric. So in our quest to relate these three concepts, what we have seen is T-transitivity leads to triangle inequality and in turn from triangle inequality we are able to obtain T-transitivity. Now what about T-transitivity and positive semidefiniteness? Are there some correspondences? Let's look at them now. Recall, this is the definition of kernel. Let's look at a particular T-NOC. It is called the T-cos T-NOC because of the generators. We will not get into the nomenclature, but this is a particular T-NOC. In 2006, Bernard Moser proved the following result. He showed that if you have a reflexive kernel, that means a kernel, by kernel we understand it to be symmetric and positive semidefinite. If it is also reflexive, just like the Gaussian or the exponential kernel, he proved that in fact that kernel looked at, we have seen that Gaussian and exponential kernels can be seen as fuzzy compatibility relations with positive semidefiniteness. He was able to show such reflexive kernels in fact satisfy T-cos transitivity and they become T-cos equivalence relation. That means with respect to this T-NOC, T-cos, they actually become a T-cos equivalence relation. So first time we are seeing that kernel can also be, at least some of these kernels can also be seen as fuzzy similarity relations or T-equivalence relations for a particular T-NOC. Now, what this means is somehow reflexivity along with positive semidefiniteness leads to T-cos transitivity. But we could also ask further questions. In a quest to help us in answering them or exploring them, let's revisit some of the things that we have seen with respect to the implications. This must be pretty fresh in your mind. If you take a T-NOC, the corresponding R implication can be defined as follows. It is denoted as IT. IT of xy is nothing but supremum of all those t's is that t of xt is less than or equal to y. Now that's the R implication. We can also obtain a by implication from a given implication, but in this case we will just concentrate on obtaining this from the family of R implications. So we'll denote it like this, IT with a double-headed arrow on top. It is defined simply as min of IT of xy comma IT of yx. So this is called a by implication. Essentially it says the minimum of A implies B and B implies A. If you consider the minimum T-NOC, we know that the corresponding R implication is the Gödel implication and the by implication obtained from the Gödel implication is almost the minimum function except when x is equal to y it is 1. Rest of the cases it is minimum. If you actually consider the Łukasiewicz T-NOC, then you get the Łukasiewicz implication and what you get here as its by implication is this function which is 1 minus mod x minus y. Perhaps this rings a bell already because in the previous lecture we have seen this function also to be an equivalence relation, in fact TLK equivalence relation. But be that as it may, presently we will just look at them as examples for by implications. Now why did we introduce these? Moser in the same paper also went on to show that if you take a reflexive kernel on X and fix arbitrarily a few points from X, the set X, say Xi, varying from 1 to n, and for each one of these indices, if you define a fuzzy set, so essentially you get a family of fuzzy sets as follows: mu A of x is equal to k of xi comma x. So now if you are thinking of a k as a compatibility relation because it's a reflexive kernel, so it is also symmetric. If you're thinking of it as some kind of a fuzzy compatibility relation, all you are doing is you are fixing an xi and you are looking at what happens with respect to that xi when you use k. How are the other elements of x related to xi under the similarity relation that you could get from the kernel k? So that will give rise to these fuzzy sets here. Now if you consider this family of fuzzy sets, he was able to show that there will exist a T norm T such that if you define E like this, infimum over this entire index set, running over this index set, the by implication is applied to these families, mu I of x, mu of y, at these 2 points x, y. If you define the relation E like this, then it will be a fuzzy similarity relation with and satisfy T-transitivity with respect to this T. That means essentially it's some kind of an existential result where we have shown that there will exist a T norm such that if you define the relation E like this, it will be a T-equivalence relation. So first time we are saying that from a reflexive kernel, you could also get T-equivalence relations. Well, we know that every reflexive kernel is T-cos equivalence relation. The question is, if you want the reverse, what kind of T-transitivity will lead to positive semi-definiteness? There's a question which has not been answered in the general, but allow me to present you some existing results. So once again, let's consider a family of fuzzy sets, start with a family of fuzzy sets, and define this relation essentially as how we have defined it earlier in the previous slide, infimum over I, this index set, but now we are using the by implication obtained from the Gödel implication. And what is interesting is, if you consider this relation EM, Clavano and Castro showed that this is in fact a TM equivalence relation. Moser, in the very same paper, showed that such a relation also satisfies positive semi-definiteness. Now, note that this is a reflexive and symmetric relation, and it also satisfies PST, which means EM is in fact a reflexive kernel. So there are TM equivalence relations which are also kernels. So it doesn't mean that kernel, a reflexive kernel, we know that it leads to T-cos transitivity, but it is not only T-cos transitive relations, equivalence relations, which will give rise to kernels. So what have we seen so far? We saw earlier that T-transitivity can be related to triangle inequality of metrics defined in a particular way, and now we are seeing that T-transitivity can also be related to the positive semi-definiteness property of the relation. Well, the last two lectures, including this, must have shown you the ubiquitousness of transitivity. In fact, if you were to take a look at the lectures that we have looked at in this week, the week 5 lectures, we have dealt with fuzzy relations, but everywhere transitivity has come up to the front. It has had a role to play. For instance, when we talked about different types of binary fuzzy relations, transitivity was very much there. When we discussed about compositions, it was again there. When we discussed about the utility or usefulness of similarity and compatibility classes in getting groupings, again we saw the important role played by transitivity, and which led us to in fact come up with an algorithm to obtain transitive relations from given fuzzy relations. We came up with the concept of transitive closure and also proposed an algorithm for it and looked at an algorithm to obtain transitive closure. So all of this has shown us the important role transitivity plays. And in this lecture, what we have seen is some correspondence between transitivity and positive semi-definiteness and triangle inequality. What next? In the next week, we will look at fuzzy relational inferences. Meanwhile, allow me to present you the works that we have referred to in this lecture. This was the paper in which Bezdek and Harris showed that TLK equivalence is related to triangle inequality of the pseudo-metric that you obtain as 1 minus c. This was the first of the papers by Bernard Dabatz and Ratko Messier, where they generalized the result of Bezdek and Harris, and they also have further results exploring the same. It would be very interesting to look into these. They have a lot more results also about obtaining equivalence relations from given metrics in different ways. This is the paper that we have referred to, showing the equivalence between reflexive kernels, or in some sense obtaining equivalence relations from reflexive kernels. This is a work that has been published in the Journal of Machine Learning Research. This is the paper by Clavon and Castro back in 1995, wherein they had shown that the relation EM that we have come up with as the infimum of the bi-implication obtained from the Gödel implication is actually EM transitive, which was shown later on to be also a reflexive kernel by Moser. Well, once again, next week we will look at fuzzy relational inferences. Glad that you can join us today for this lecture. Looking forward to meeting you again soon in the next lecture. Thank you.